In this video, we will look at resistors in series and parallel. We will discuss the combination of resistors that are connected in series and parallel. In doing so, we will introduce the concept of equivalent resistance for a particular network of resistors. In calculating the equivalent resistance, we shall look how the current and voltage are distributed among these resistors. We will then look at some solved problems to highlight these concepts. Let's look at two resistors in series as shown by this diagram. So you have resistor R1 and R2. Now these resistors are connected to a battery like that. Let's call the EMF of the battery E. So obviously this is a positive terminal and that's a negative terminal. So the current that comes out of the battery, the positive terminal of the battery, is I. So it will go in that direction, I. It will go through the first resistor, R1, and the same current will go through the second resistor before it comes back to the negative terminal. So the first point about two resistors in series is that they carry the same current. So current in two resistors in series are the same. The second thing is about the voltage. Let's assume the voltage across R1 is V1 and voltage across R2 is V2, where we know that V1 is quite simply I, the current through that resistor, times the resistance of that resistor, according to Ohm's law. Likewise, V2, the potential difference across R2, is the current through it, which is I, times the resistance of that resistor, namely R2. So point number 2 about two resistors in series is that the voltage across them, V1 and V2, they sum up to the original EMF of the battery. So in this case, V1 plus V2 must be the same as the EMF of the battery. So we say potential difference add up when we consider resistors in series. Now let's look at the concept of equivalent resistance for two resistors in series, such as R1 and R2 here. Let's assume that we can reduce this circuit with two resistors into a circuit with just a single resistor, like that, everything else being the same. So this is the same battery with the same EMF E. Let's assume the resistance of this single resistor is Req. The question is, if you want to have these two circuits to be equivalent to each other, what must the value of Req be in terms of R1 and R2? If you want the two circuits to be equivalent, the same amount of current must be on the second circuit that's coming out of the battery, namely I. Now we have seen that the potential difference across R1 and R2 must add up to the EMF. So in the first circuit, we can simply write EMF equals I R1 plus I R2, this being V1 and that being V2. In the second circuit, the equivalent circuit, EMF is quite simply I R EQ. Since these two EMFs are the same, we can equate them and we get this equation. The I cancels out because it appears in all the terms, and immediately you see that we obtain an equation for Req as quite simply being R1 plus R2. So this is the equivalent resistance for the circuit. It is quite simply the sum of the resistance of the resistors in that circuit. Let's generalize this result. instead of 2 resistors, let's say you have n resistors in series, like that. So the first resistor has resistance R1, R2, R3, all the way to Rn. And we want to create a circuit with just a single resistor with resistance Req. So in this case, the equivalent resistance Req is quite simply the sum of the original resistances. So R1, R2, all the way to Rn. So this is the generalization of equivalent resistance for any number of resistors in series. Now let's look at resistors in parallel combination. So let's say now you have 3 of them in parallel, like that. So this is R1, this is R2, and this is resistor R3. And they are connected to a battery like that, and the EMF of the battery is E. Let's first look at the current distribution. So that's a plus and the negative terminal of the battery. So the current I will originate from the positive terminal of the battery. It goes all the way there, and then it will start to branch out into 3 segments, like that. So there is a current I1 through resistor R1, current I2 through the resistor R2, and current I3 through the resistor R3. And all of these currents will recombine back into I and comes back to the negative terminal. So clearly you can see point number 1 about resistors in parallel. The currents add up. The currents in all the resistors in parallel add up to the original current out of the battery. That's point number 1. Now let's look at the potential difference across these resistors. The potential difference across resistor R1, let's call it V1. V1 is quite simply I1 times R1. Likewise, the potential difference across R2, let's call that V2, is I2, the current through that resistor, times the resistance of that resistor, according to Ohm's law. And finally, the potential difference across resistor R3, let's call it V3, is quite simply I3 times R3. So the second important point is that the potential difference across R1, the potential difference across R2, and the potential difference across R3 all are parallel to each other, must be the same as the EMF of the battery. So point number 2, the EMF of the battery must be the same as V1 equals to V2 equals to V3. So that's point number 2 for resistors connected in parallel. Now let's look at the concept of equivalent resistance for resistors in parallel. So let's go back to the circuit that we have just sketched a few minutes ago, where you had 3 resistors in parallel, like that, R1, R2, and R3, and the EMF of the battery is E. So the original current is I, the current through R1 is I1, current through R2 is I2, and the current through R3 is I3. Suppose we want to reduce this circuit into a circuit with just a single resistor with resistance Req. Everything else be the same, so the EMF of this battery is E, and the same amount of current is coming out, that is I, and passing through the resistor Req. So these 2 circuits were to be equivalent. What Req should be? The resistance of that resistor, the single resistor on the right, in terms of R1, R2, and R3. How do we express Req in terms of these 3? Note that we know I equals I1 plus I2 plus I3. We have explained that a few minutes ago. From the equivalent circuit, we know I is quite simply the EMF over Req, the resistance of that single resistor on the right. So rewriting these results, you get EOREQ equals, now I1 is quite simply V1 over R1. But we know V1 is quite simply the EMF. So we can simply write like that. And the same goes for all the other currents, EMF over R2 plus EMF over R3. So the E's will cancel and will give you the following result for the equivalent resistance of this circuit. 1 over equivalence resistance equals 1 over R1 plus 1 over R2 plus 1 over R3. So this is how you combine resistors in parallel connection. To generalize, if you have n resistors in parallel and the equivalent circuit consists of just a single resistor with resistance Req, then 1 over Req is quite simply the sum of the inverse of all the resistance that appear in the original circuit. Like that. Let's look at the following simple exercise. You have an original current 2 ampere coming in and branching out into I1 that goes through 1 ohm resistor and I3 that goes through 3 ohm resistor. How do you find I1 and I3? The first thing to note is I1 plus I3 must add up to the original current of 2 ampere. So that's equation 1. The second thing to note is that potential difference across 1 ohm resistor and 3 ohm resistor must be the same because they're connected in parallel. So we say I1 times 1 must be the same as I3 times 3 according to Ohm's law. Potential difference across a particular resistor is the current times the resistance. So that is equation 2. Placing equation 2 into equation 1, we get 4I3 equals to 2. So I3 is half ampere. That means I1 is 3 over 2 ampere. And that solves the problem. Let's look at the following problem. 4 resistors are connected as shown below. 4 ohms, 8 ohms, 3 ohms, and 6 ohms resistor. Find the equivalent resistance of this network and the current through each resistor if the potential difference across points A and B is 40 volts. So let's do part A. First, let's combine the 3 ohm resistor and the 6 ohm resistor. The result of combining the 3 and the 6 ohm resistor will result in a circuit like this. So this is a 4 ohm resistor. This is 8. Let's call this R36. This is equivalent resistance by combining the 3 ohm and the 6 ohm resistor. Now we know how to compute R36. Is 1 over R36 is quite simply 1 over 3 plus 1 over 6, and that's half. So that means R36 is 2 ohms. 2 ohms right there. Now to combine these 3 resistors in series into one is easy. So R equivalent of the entire circuit is just 4 plus 8 plus 2, which is 14 ohms. And that's the answer for part A. Now the current. The same I will go through 4 and 8 ohm resistor. This I will split into 2. Let's call it I3 and I6. The potential difference is 40 volts. So the current through 4 and 8 ohm resistor is quite simply, according to Ohm's law, 40 over 14. 40 over 14, which is 20 over 7 ampere. Note, this I must be the same as I3 plus I6. So that's equation 1. Potential difference across that and that must be the same. So I3 times 3 equals I6 times 6. So that is equation 2. Simultaneously solving these two equations for I3 and I6, we have the following. I6 being 20 over 21 ampere, and I3 is 40 over 21 ampere. Note that these two sum up to that, and that solves the problem. Thank you for watching.